Hello and welcome everyone. My name is Mark Henry, and in today's Augmentic webinar series, we'll be talking about configuration and fault management for telcos and service providers. During today's session, all attendees are going to be on mute. We will have a Q&A session at the end where we'll be turning off the recording and allowing you to ask any questions that you might have. Topics today, we're going to be talking about how to use trending data to intelligently adjust for fault management. So we're going to do a compare and contrast between NMIS's static thresholding system and Opie trends trending data. We're going to talk about how to reduce event noise through effective consolidation, deduplification, prioritization, and storm management using Opie events. We'll talk about integrating and scaling configuration management using Opie config. And we'll talk about how to automate event response for maximum effectiveness and reduction in manual efforts, again, using Opie events. So let's talk a bit about why we want to talk about this subject, why this subject is so important to network engineers, but just not engineers themselves, engineer managers, department heads, and IT groups as a whole. Really, if you look at the ITIL service model, specifically the service management maturity model, most groups that we talk to are somewhere between level 0 and level 1. Where they really want to be heading into is more towards the level 3 of service management. And what that requires, you'll see these darkened areas for each of these levels. To begin with, you've got to have alert and event management capability. You have to be able to measure component availability up and down. Of course, you can do that with Augmentec's core NMIS performance and fault management solution. But to get you to level 2, you have to be able to start analyzing trends. You have to be able to set thresholds dynamically, predict problems. You need to automate response. And then at that level 3 piece, when you start talking about performance fault management, you have to be able to measure and report service availability. And so the pieces that we're going to talk about today really help support those requirements within the service management maturity module. And of course, those all drive you towards increasing performance and value to the organization. So there are several goals that really drive event decision making. That starts out with the concept that you're going to manage measurement and thresholding intelligently. That most large enterprise class customers want to be able to capture event details from all events. You want to be able to conduct troubleshooting and remediation automatically. So you don't want to necessarily have to wait for an engineer to get a ticket. You want the system, the computer, to intelligently start responding to events as they're occurring live. You want to be able to assign priority based on client direction. So all of Augmentec's tools come with built-in priority management, but you may want to map that built-in priority numbers to your own internal priority tracking system. And then, of course, you want to be able to alert the correct resource in a timely manner. So whether that's generating email to an engineer, generating an SMS text message, calling a phone number, waking up the on-call person, pushing a ticket into a help desk system, reaching out through an API and executing some kind of a transaction. Whatever that is, you want to be able to do it in a timely manner. So let's talk about architecting the solution and some of the parts that come into that. So at the core is Augmentec's NMIS, Network Monitoring Information System. Again, that's handling all of your performance and fault monitoring. It's included in the solution is OPHA. Included in that solution is OPHA. Apologies, everyone. My computer's going crazy today. So included in that solution is OPHA, Opie events, and Opie trend. So the type of scaled server architecture we're going to mention today is the concept that you have a multi-tiered architecture where you have polling servers or NMIS collectors at the bottom layer, interconnected using OPHA to talk to one or more master servers at a secondary layer. So each of the pollers are collecting from their own subnets, their own regions, their own geographic regions, or maybe even their own vertical type of equipment. So we have several clients who break out pollers by networking devices and servers. We have others who break out their equipment by subnets. We have others who deploy pollers in geographic regions and gather equipment within that geographic location, east of the Mississippi, west of the Mississippi, Western Europe, etc. So the way that that kind of data flow looks when you're looking at NMIS, you're looking at the concept of NMIS itself, polling subnets, gathering information from devices, passing that to OPHA, which passes that to the master server's version and makes that information available to NMIS. NMIS also makes events available to OP events. OP events gives you a higher level of event processing than NMIS's native escalation rules do. And then that information is passed on up to OP events on the master server. So let's talk about how to leverage trending data to intelligently adjust for fault management. So down the left-hand side here, we're talking briefly about NMIS's static thresholding. So NMIS, Network Monitoring Information System, includes 5 different levels of thresholds that are predefined within the common thresholding file. So every type of device, every manufacturer, model, or type of device, whether it's router, switch, hub, firewall, server, etc., has series of thresholds defined for each of the parameters that are being collected for that device. So you have normal, anything that's a normal situation for that device or a normal range. Then you have warning, minor, major, critical, and fatal. And those could be rising or falling thresholds. And you can actually combine those. For example, you might have rising thresholds for bandwidth, for interface bandwidth measurements, where a warning might be 60%, minor might be 75, major 85, critical 95, fatal 99%. But you might also have a falling threshold where you may say that you want an alarm set for a warning at 10, a minor at 8%, a major at 6%, critical at 2%, and fatal at 1% of usage. Now, these are all static thresholds. They could be related to the actual measurement, so packets, bytes per second, kilobytes per second, megabytes per second, or whatever the value that's being captured is. They could also be threshold levels set on percentages. So percentage of use, for example, in the bandwidth example I just gave. And it's important to understand that irregardless of the type of device that you're looking at, the events are normalized across similar OIDs and manufacturers. So CPU performance, CPU usage, for example, is normalized whether it's a firewall, a router, a switch, a hub, etc. They're all normalized into one set of threshold components. And then from there, they can be broken up and focused in on based on the type of device, class of device, location of the device, the customer even, or the device name. So you can be very, very specific if you want to as well. Now, Opie Trend builds on that concept of NMIS's static thresholding by gathering 26 weeks of performance data. It then compares the day of the week in 1-hour windows. So, for example, today, the day that we're recording this webinar, it happens to be Tuesday, February 13th, and it's 2 p.m. Eastern time in the afternoon. So Opie Trend is going to look at every Tuesday from 2 to 3 p.m. for the past 26 weeks and create a standard deviation chart. And using what's called a SEDS algorithm, it's going to determine what's normal operation for each parameter on each device at that hour on that day of the week. So if I'm collecting CPU data, memory data, interface data, in, out, errors, discards, etc., Opie Trend is going to capture each of those parameters and compare that 1-hour window on every Tuesday for the past 26 weeks and create a bell curve for that to determine what's normal and what's not. Opie Trend can be used to enhance NMIS's static thresholding or completely replace it. So generally speaking, when clients are implementing Opmantic's network monitoring systems, what we recommend is we configure Opie Trend to gather data but not generate alerts for about the first 2 to 3 months. So we want to gather anywhere from 8 to 12 weeks of data to begin with to kind of feed Opie trend. Meanwhile, NMIS static thresholding is generating all of your alerts. At some point, you turn on Opie Trend's alerting module, and as it gathers more performance data over wider ranges of time, heading out toward that 26-week window, then Opie Trend will become more and more automated and intelligent in the way that it responds. The standard deviation window, the bell curve of what's acceptable both in high and low performance, will get more and more specific for each hour on each day for each measurement of each type of device. So let's take a quick look at NMIS. Over on the left side, we have a small example of a NMIS model. So we'll be talking next month about NMIS modeling and how NMIS modeling is done and how you can create models for your own devices or adjust NMIS's built-in models. But in this example, you'll see that we're monitoring in the section node health. We have several different graphs that are being defined, and then we have several different pieces of memory, routing, and average busy time for CPU being captured and graphed. On the right-hand side, you'll see the common thresholding system, where we're taking that CPU section, we're giving it the name proactive CPU, so we're normalizing everything. And in this example, we're taking the average busy 5-minute value from the model, and we're mapping it to proactive CPU. So the alert, the event that you'll see will be called proactive CPU rather than average busy 5-minute. Below that in the control area, you'll see that we're looking for a role type of core. NMIS comes with several different role types predefined, core, distribution, etc. So in this example, we're saying that for every device assigned to a role type of core, these are the values that we want to apply to those static thresholds. So again, warning, minor, major, critical, and fatal. You'll notice that critical comes first in this list. They're just alphabetized in the list here. But remember, you want to continue these having in this case, it happens to be a rising alarm. So the first alarm would happen at 30%, the next alarm at 40%, the major alarm at 50%, the critical alarm at 60%, and the fatal alarm at 70% for proactive CPU usage. Now, again, these are static, so you can create as many of these as you want for as many different controls. You can create additional controls for type of device, location, customer, even for a specific device. You may say device name equals some string. You may set up different types of thresholds for different customers. So if you're working as a managed service provider, you may have one customer that says, look, we only want to know when these devices are absolutely dead and burning and turning into charcoal. And so raise all of the alarms to 95, 96, 97, 98, 99% and leave it at that. And don't wake us up for anything that's less important. Totally up to you, very, very flexible. But again, these numbers don't change. So they're not based on how the device is actually performing or what the normal load is on that device. These are just static numbers that are stored and then compared during each collection cycle. So taking a look and comparing that concept to Opie trend, on the left-hand side, you'll see an example of the Opie trend dashboard system. You'll notice that there are devices moving up and down within the CPU space. The number one list happens to be the BNE Server 1 CPU. And on the right-hand side, you'll see the presentation for what that actually looks like. So for example, the blue lines give you the upper and lower. The bell curve is what exists within that line. And what I mean by that is the green line is the mean. And then the black line itself is how that device is performing actually at that moment in time. So the blue window is what the system expects from the device at that moment in time on that day of the week that this example screen capture was done. And then the purple bands indicate anywhere where actual device performance or measured point performance, in this case CPU, exceeded that window, exceeded that expected window. So again, Opie trend doesn't rely on device or manufacturer specific thresholds. It's working and looking at what is normal for that device on this day of the week between a specific window of hours and how well that device is performing. And then Opie Trend can actually raise an alert from Opie Trend into Opie Events, and it can be responded to in Opie Events. So the next piece we're going to talk about today is how to reduce event noise. So you have all of these different events coming in from your performance monitoring system. Thresholds are being run, OP trends being run and generating events. A lot of things are happening. You happen to have a power outage in a region. Someone pulls a plug on a rack out of the wall by accident. Systems are rebooted. You might have a lot of network traffic today. Bandwidth usage goes through the roof. And how do you manage that noise? So in NMIS, every single event is handled individually. There's no correlation, there's no deduplification. There is some storm control, there's some basic handling of flap in NMIS, there's a basic concept of it. But really, if you're looking to handle things like blacklists, whitelists, correlation, deduplification, you really want to look at Optmentech's OP events to enhance NMIS and take over event management. There are several steps to how OP Events processes each and every incoming event. And so this is illustrated on this chart. The first thing it does is it applies an archive list. What records should be kept for what types of events? Then it applies a blacklist. A blacklist is just what it says. These are events or types of events, classes of events, or even device types that events should never be processed for. OP Events then applies a whitelist. That's a list of events that should always be processed and should always have a priority. Finally, events are correlated into outages, and we'll talk about that in detail in a minute. Events are then deduplicated. So for example, if an event is, if you have a node reporting node down, so it's going down and up, down and up, down and up very, very quickly, the system deduplicates those events and rolls them up into an event flap. So in a way, it's a correlation of events, but it's also deduplicating all those individual pieces and rolling them up into one master piece. The last thing that happens is determining priority. So what's the priority of the events? It then conducts any actions. Those are the automated responses, whether they're troubleshooting or some kind of a proactive response to an event. And then it starts escalations, meaning what's the policy for notifying people, at what time periods following the event do those escalations happen. So some background pieces. The whitelist, blacklist, and archive rules are all contained in the eventlistrules.nms file. The correlation and suppression rules are all contained in eventrules.nms. The priority, escalations, and actions rules are all contained in eventactions.nms. We're going to touch on each of these files in detail in just a moment. So correlation rules. How do I correlate events together? It's important to understand that OP Events does all of its event correlation based on time. So OP Events looks at a window of time, a number of seconds, a number of minutes, a number of hours, and says what things have happened within that window of time and are they related? Can they be related? So for example, a correlation rule might be a location outage. So if OP Events is processing events like node down, service down, SNMP down, and sees those types of events from 5 or more devices within a 60-second window coming from the same location or assigned in the same location, then it will group those together, and rather than reporting the individual events, it'll report a single location outage and roll all those events up into one event. You can do the same type of thing for a customer outage. So if you have devices assigned to an individual customer, and again, OP Events sees node down, service down, SNMP down, sees 5 or more devices within 60 seconds, all assigned to the same customer, pull those all together, correlate those all together, and roll them up into a customer outage. Again, the concept is so that you reduce the number of events that are individually being processed by OP Events and roll them up into something of a higher priority. You can do the same thing for devices within specific groups, or as the bottom rule example gives, a major disaster, where you have a network outage, and that network outage, if you have 4 or more of them, roll that network outage up into a major disaster or a regional disaster. So just different examples. These, again, are all defined in the event rules list. So you can actually go in and adjust these yourself. You can comment out whichever correlation rules don't make sense to you. You can build additional rules. You can add or remove what types of events or are correlated together to create the rule, how many devices it takes, or what amount of time you might look at to create that. It also includes suppression rules, and we'll talk about Opie config in a minute, but the concept that if an individual device is reporting multiple configuration changes within a small window of time, you might want to suppress those individual changes and roll them up into just one notification that there's been a change. So if someone's configuring a device, making multiple changes to that device, rather than raising alerts for every single command change that might have happened, just raise one event for it. So integrating and scaling configuration management. So with the ever increased pressure on network teams to monitor not just performance of devices, but security considerations. Has someone hacked into a device and changed the default configuration or the approved configuration of that device? Has someone, perhaps a remote or field technician, deployed a new device that wasn't configured correctly or left it configured in an unacceptable state? So in order to gather that information, you first have to start talking about things like when and how are we going to collect device configurations. And that starts with understanding what commands you will execute. In opconfig, the way opconfig works is by either using telnet or SSH to connect to a device, using a set of credentials that are provided and stored encrypted in the database to log into that device, and then based on that device's manufacturer, model, and operating system, executing very specific CLI commands on that device, and then capturing the results of those CLI commands and comparing those against the last stored set of CLI commands and determining if there's been a change from one running to the next. These types of commands can be run on a daily or hourly schedule. It's all run through a cron job. You can define individual commands based on how often they should run. So you might create commands and say that, for example, show running config, you may want to capture daily and hourly, and you may want to use it for troubleshooting. So there are various types of tags that you can put on each command for each type of, again, manufacturer, model, and even operating system. And then in addition to scheduled collection through a cron job, you can also use op events to execute a command in opconfig to capture information about a specific device. So if op events has seen an event, something's changed, maybe BGP tables have changed, and you want to collect that information from that device and then determine if you need to alert on it, you can absolutely do that as well. And that becomes an op events action. So how long do we store these revisions? So these are base policies. They're all set up in config. So it's in the opcommon.nms file. You can change any of these. You can change them however often you want. It's important to understand that if a configuration change has been discarded, if it's not been kept, you can't get it back once it's been deleted. So by default, opconfig will retain the first and the most recent revision indefinitely. It'll retain any revision marked as protected indefinitely, and it'll retain the last n number of revisions of each command that's run. The default for that's the last 100 revisions, and it will purge unprotected revisions older than 365 days. So if you're going to only hold 100 revisions, but it has 90, after 365 days, any of those 90 that are not marked for as protected will be deleted. So let's take a look. I'm just going to sequence over here. Let's take a look at what Opie config command output looks like as an example. So you can see here on the left-hand side, what we've done is we're capturing show running config off of Asgard, which is a small Cisco iOS router. And you can see here, for example, in the green, that's the newest change, and the red is the old version. So you can see this is a change that we would want to be alerted on. So for example, someone has changed service password encryption and service sequence numbers and reset the system for no service password encryption, which means the password for that device is now stored in clear text. That's no bueno. We would absolutely want to know about that. You can see in the top right-hand corner that this change has been protected. We want to make sure that this doesn't get overwritten. And we're keeping track of some basic information here as well. Date and time that this was collected, date and time that this changed at, the last time it happened, how many changes are being stored, etc. And if we move forward to the most recent revision, let's see what's happened in revision number 200. You can see that no service password encryption is still set. The date and time has changed. And I believe if we look further down, there's been a change to a tunnel destination as well. And that may be, again, a piece that you'd want to have a raise an alert for. So that's all pre-configured right out of the box, but you can expand it. You can add additional commands to be captured and collected. You can add support for additional devices. It's all completely covered in the Opmantic wiki for the Opie config solution. So how does alerting occur from Opie config? So in the example of NMIS raising an event, so NMIS detects a change, and that could be OP trend reporting a change to NMIS. NMIS creates an event. That event then goes to OP events. So OP events receives that event. OP events directs OP config to collect whatever commands are necessary. So OP config then executes that command collection. OP config compares the results of the collection, and then OP config links the results of that collection back to the event that occurred. So again, if you have OP events running and you have OP config running on the same server, they're interconnected automatically. OP events can generate through event actions the collection of a configuration of a device based on whatever criteria you want. And we'll touch in a minute on the different criteria that we have and the types of commands that are executed under event actions, again, right out of the box. So how does OP config collection work if it's queued from a cron job? So again, the thought process of collecting configurations every hour or once a day. So a cron job runs. OP config executes command collection. It might execute the hourly command collection. It compares the results of that collection, those commands, against the previous version. If there is a change, if there is a substantial change in the results, and that event is raised from OP config, it'll actually generate an event that'll raise and link back into NMIS. OP event, it'll go from NMIS to OP events. OP events receives the change event. OP config links the results of that back to the event. So you'll still have that concept that a change has happened in a configuration. This is what the change was, and these are the things that are important that need to be dealt with. Common workflow in using OP config with OP events. So you start by identifying the device, the event, the element, the priority. You investigate revisions and change control, add comments and acknowledge the event, and close the event out. And then through remediation, you have after action, actions, and correlation. Again, this is just kind of a starting point for internal discussion. How do you want to handle config changes or actually any event in OP events? If you want to know more information on OP config or OP events, we will be holding seminars, webinars during the month of March and April that will focus in specifically on each of those products individually and talk about how they work. So how do you automate event response with OP events? So the concept basically is what criteria will create an event action. So right off, it's event actions available for all events meeting specific criteria. It's applied regardless of the priority. So generally speaking, we don't look at the priority if something's a priority 1 or priority 4, 10, 3, whatever, in running an event action. So it's based on the event itself. If you're doing a multi-tiered delivery, events are handled by the polling servers. You really want event actions happening by the device or by the collector that's talking to the device that's generating the event. And you want the results of that action stored with the event. We'll show you that in just a moment. For implementation, you want to do event actions to start off with. What we ship with is about a dozen troubleshooting actions. And then you want to think about what is remediative. So for example, if you always have a process that you run in response to a specific type of action, for example, you may have some homegrown software that ends up eating up memory on a server and the service goes down. And so your engineer's response might be that when the service reports down, log into the server, restart the service. If memory stays high, you may reboot the server. So if you can map that out, if you can just list those steps, those can actually be replicated in an event action. So before we get into the list of what ships, let's take a quick look at what one of those looks like. So here we have an event in OP Events. So you'll see in the top left, we've got the name, the host, the group it's assigned to, the event itself, proactive CPU IO wait. The value is 3.64. The threshold is 3. And it's been assigned a change number. If I look down, you'll see that a script ran, TS Linux disk IO. The script took 24 seconds to run from start, and it completed successfully. So exit code 0 means good completion. Exit code, exit code anything else, but generally 255 means that the script failed. And if I scroll down, you'll see the results of that output from that. TS disk IO is stored at the bottom of the page. And you can see that this is actually the direct CLI output from that, from running that. So it even gives you a copy of what command was run. Command output for top -N3, -D3, -M, -B. And so you get the output for that, and that's all stored here and attached to this ticket, so that by the time the engineer can come down here and start troubleshooting this, they'll have all of this additional rich information available to them to be able to take a look, see how this device is doing. And you can see in the top right corner, you can see that this event has happened many times before. In fact, within just the last 2 hours of this event, you can see that it's happened 1, 2, 3, 4, 5 times. And each of these should have this same event action run and this same data available for analysis by the engineer. So OP Events ships with all of these event actions pre-built into it. So it's in response. The underlined section is the event, and then the actual actions being taken are shown under it. So for example, for proactive CPU on a Cisco device, it'll run show process of CPU sorted, show IP flow top talkers. For proactive interface output utilization, it'll run show IP flow top talkers, et cetera, et cetera. Down at the bottom, you'll see for role type distribution and stateful equals BGP neighbor, it'll run a ping. In fact, it runs 2 different pings to 2 different types of devices, and then it'll run show IP BGP, show IP BGP summary, and show IP route summary. Those last 3, of course, require OP-config to be installed, and for that device to be licensed in OP-config, as well as a set of credentials to exist in OP-config in order for those three commands to run and output to be stored. These are really provided as a starting point for you. It's a point of conversation. So if you're licensing OP events but not OP-config, you'd want to comment out the actions that require OP-config. If you don't rely on Cisco devices, but you want to run similar commands on Juniper or Huawei, Radwin, etc., then you can build this out. It's very, very easy. It's very, very straightforward. You can build commands that can be called from many different individual events, many different types of events. Again, whether it's calling an outside script, anything that can be run from a Linux command line can be run from an event action. It's really that simple. So in conclusion, I know we talked about the concept of large-scale, fast deployments and how these types of fault and configuration collection systems can support those. At the heart of it is the concept that all of these configurations, all of the policies are all stored in configuration files and external configuration files that can easily be managed and manipulated using common DevOps procedures. This allows you to deploy new polling servers, configure those polling servers to your standard, adjust those configurations based on that specific polling server, and even add devices to that polling server, all via scripts, and whether that's, again, through a DevOps procedure or through some kind of a north or southbound interconnection to like a CMDB like ServiceNow to be able to populate the devices that go on that polling server, and then have that polling server report up to a master server and just have it work. Augmentech solutions support all of that, and they support it at large scale. So again, my name is Mark Henry. I thank you all very much for your time today. I wish you well, and I look forward to seeing you again at next week's session. Thank you.